Okay, that's 11. We can start. So today I will post the next homework about chapter 6. Today we will finish chapter 6 about calculus of variation. So yeah, and I will post this. There will be like 4 problems approximately. And this is probably one of the easiest homeworks. Very straightforward. Just need to get through calculations. Okay, anyway, so back where we were. So in the previous class, we started refreshing, right, reviewing calculus of variations, because at this point everyone should be familiar with calculus of variations, right, somewhere in the calculus classes. And so basically calculus of variations allows us to find some curve along which an integral, which we call functional, has a stationary value. It can be minimum or maximum. We cannot guarantee that because, yeah, the way we derived the Euler Lagrange equation, we cannot bet all our money on the fact that it will be minimum or maximum. Right? So, of course, you need to do some additional work in order to convince yourself in that. But we're not going to cover that. All right. In all the problems which we are going to discuss, the path which we are going to find will minimize our functionals. Right. Okay. So let me sort of quickly review. So if you, yeah, I was planning to write something. Okay. All right, so in the previous class, so if you have some functionals, right, so for example, S, which is the function of y, y prime, and x, right? Prime, it's a derivative with respect to x, of course. Right? And this functional is presented like this. Let's say an integral from x1 to x2, some integrand, which is a function of y, y prime, x, dx, so that is functional. Right, and so what we need to find y as a function of x, so that the path, the function y as a function of x, along which this function is stationary, right? And we derived this equation. We derived the Euler Lagrange equation, right? So where you just need to grab the integrand and drag it through this second order differential equation, right? df over d y minus d over dx and partial derivative of f with respect to y prime equals to 0. And I want to emphasize on one important piece, because you will see why. This is our independent variable, x, in this case. So that's our independent variable in this total derivative. Independent variable. And then, of course, y, this, right, and y prime are dependent. Oops. Dependent variable. Again, as I said, maybe in 10 or 15 minutes, you will see why I'm emphasizing that this is dependent and that is independent variable. And so this is what we call the Euler Lagrange equation, second order differential equation. You know what? Probably it's time for me to change the marker. Yeah. It's still fine, but it's getting brighter, lighter. Right. Okay, and then we looked at one example. Right? So we looked at 2 points in a plane, and we proved that the shortest path between any 2 points in a plane is a straight line. Of course, we knew it from the very beginning, but now we have a tool which can help us to get that automatically. And then you can apply that tool for any more complicated problem. Okay, so that's what we got in the previous class, and now let me separate this, and oops, it needs some time before marker start writing better. New one. Okay, so now the example, next example. Let's look at the Brachistochrone problem. Oh my God, let me, I will try to spell it right. Brachistochrone, yeah, problem. Typical problem. Most of the books discuss that. Right. Okay, so what is this problem? What do we have in this problem? All right, so let's assume that this is some initial point 1, and this is final point 2. And of course, the whole system right now, okay, I haven't presented the system, but let's say in this space, there is a field of force of gravity, gravitational force just near the surface of the Earth, mg. Right, so of course we have acceleration due to gravity, g, downward. So now the problem is, we want to release some object, let's say maybe a roller coaster car, from point 1, and we want to find the path, basically function, path, so that when this car moves from this point to that point, it will take the smallest amount of time. So the cart will move the fastest from this point to that point. Again, the cart is released from this point, from the point 1. Right. So in the shortest possible time. Maybe let me write this. So we want to build a track, basically a roller coaster track, so that a car released from point 1 would reach point 2 in the shortest possible time. Okay, the marker is getting better after just 3 lines of writing. In the shortest possible time. Okay, I need this space. I will write it here. In the shortest time. Right. Okay, so that's the problem. And now we have a tool, and we can apply it again. So first step, you need to set up the functional, some kind of integral, right? And then, of course, once you do it, grab the integrand and drag it through this Euler Lagrange equation. Right? And so in the previous example, we minimized what? We tried to minimize the distance, basically length between 2 points. Now we are going to minimize time. Right? So you can minimize anything, right? You can minimize your income, you can minimize distance, you can minimize potential energy, you can minimize, I don't know. Basically, it can be applied for any problem. Okay, so let me add a few lines. So first of all, coordinate system. Let's say this is my y-axis. This is x. Right? Again, as in the previous example, we just need to take a completely arbitrary path. Right? Completely arbitrary path. Right? So let's say this is arbitrary path. Right. And so let's write down the integral. So tau, let's say that's the total travel time along this arbitrary path, which of course we need to optimize to minimize the travel time. Tau, of course, it's an integral of d tau, and of course integral and d tau we can write so which way. So if we take this ds, infinitesimally short part of this or section of this path, so it will be ds divided by the velocity at this path, right? So let me emphasize that also v naught equals to 0, right? The object was released, right? And so now ds, it's exactly the same expression like what we had in the previous example, right? Okay, I will write ds later. Now let's find velocity at this ds, right? In order to find that velocity, we can use conservation of mechanical energy, right? So v and use conservation of energy. So basically, E1 equals to E2. So in order to write this up, right, so first we need to make a decision which point, where is our reference level. I will position it, makes sense. Potential energy 0 over there, right? So it will be K or T we used. Again, I just had physics 2, and again I'm confused. I think T. We use in this class T. Yeah, damn it, right? Because we just recently also used energy approach in physics 2, and there we use K, and now kind of something flipped in my brain. Right. So T minus U, T1 minus U1 equals T2 minus, why minus? I already moved to Lagrangian Formalism, plus of course. So kinetic energy is 0, so this is 0. Potential energy is also 0 at 0.1. And of course, this side, we can write, so 0 equals to mv squared over 2. And potential energy is negative because it's below our reference level. You remember, if you pick the reference level, if an object above, potential energy positive. If an object below, potential energy is negative, right? So in this case, it's below the reference level, so it will be m minus mg y. And y, of course, that's the position where that small section is. Okay, so of course
that's true even though y is pointed downwards?
I don't care. I just know from physics, so if this is my reference level, potential energy equals 0. If an object above, potential energy is positive. If it's below, potential energy negative. Potential energy doesn't care where your reference point is. You can pick y up or down. But in this case, of course, you need to remember the way I explained. In that case, your y or h is just a distance, absolute value, from the reference level to the point where the object is or the system is at that moment, right?
Okay. Thanks.
So basically, it's like two independent things. So you have coordinate systems, which you can use to define position, right? And then you can treat independently potential energy, your reference level, and then mg y. But y, of course, is just a distance from the reference level to the point where the object is. If it's above, positive. If it's below, negative. Right? Mm-hmm. So from here, velocity will be equals just square root of 2gy. Of course, we knew it from the very beginning, right? You remember it from. So v equals square root of 2gy, right? Okay, so now we can plug it there. Okay, you know what? I will probably write it below. So tau will be equal. Square root of 2g I will take outside of the sign of integration. 1 over square root of 2g, right? Then integral. ds, it will be dx squared. Okay, I can show that. This is dy, this is dx, right? And like in the previous example when we discussed minimization the distance between 2 points in a plane. So dx squared plus dy squared, right, and divided by square root of y. And I'm still not writing the limits explicitly. I will just put point 1 and point 2 because right now we have to make an important decision. We have to make an important decision. Which decision? Okay, maybe you know what. No, I will frame it later. Right now it's not final product. Now we have to make a decision. Which variable we're going to treat as an independent one? Basically, if you take dx outside of this square root, and you will have here dx. So it means that you're going to treat x as your independent variable, and that's your variable of integration, right? And then you will be able to put the limits. But at the same time, you can pull out dy out of the square root of the square root. In that case, basically it means that you treat y as an independent variable, and of course you will here put y1 and y2. So which variable should we take as an independent? Let's try both. It doesn't mean that I will solve the whole problem using this as independent and that as independent, but you will see at a certain point we will stop and realizing that this approach is easier than that, and significantly easier. Okay, so now let's discuss this dilemma. All right. So now we have a dilemma. X or y as an independent variable. And I will put a big question mark. Okay, so now let's look at both of them. So let's start with, for example, x as independent and y will be in that case dependent. So first, all right, so x independent and y dependent. In that case, our functional is going to look like this. So again, 1 over square root of 2g variable, integration from x1 to x2, right? And so we will have in that case square root of 1 plus y prime squared over y and dx, where y prime, of course, it's a dy over dx. So in that case, so this is our integrand, right? So this is our function f, right? So that's our f. In this case, it's a function, of course, y prime, and x is not there, right? So that's our f. And so now our Euler Lagrange equation, in that case, will be Euler Lagrange equation, partial derivative of f with respect to dependent variable, independent variable. So in this case, x is independent, so we have to just rewrite this equation. df over dy minus d over dx, partial derivative of f with respect to y prime equals to 0. And now let's look carefully at this equation. df over dy, this df over dy, our function f is a function of y, right? You see, it's a function of y prime and y. So it means that this partial derivative is not 0. Oops. Let me frame it like this, right? And I will emphasize it's not 0. And I will put a big sad face. Why? It means that in this case, we have second order differential equation. Like in the previous example, right? You remember this derivative was 0, and basically it allowed us to integrate, to make a first integration without any problems, without any sweat. But now that derivative is not 0, And again, it's not wrong. Nothing is wrong with this, except that you will have to solve second order differential equation. So you have to integrate it twice, and it will be painful. It's not undoable, but painful. Now let's look at the second situation. What if we treat y as an independent variable? So again, nothing wrong with that, but if there is an option, easier option, why not? Let's explore the second. Second option. So what if y as independent and x is dependent variable? In this case, integrand will be, the functional equals, so integral will be now from y1 to y2, and we will have now 1 plus x prime squared over y. If you take dy outside, you will have dx over dy. Dx over dy is x prime. Okay, let me emphasize that here. X prime, it's a dx over dy. And of course, yeah, dy outside over here. So now this is our function f. So this is our function f. And my speakers, I hate them when they start talking, especially in the middle of the night. It's scary. So now we cannot just rewrite. And now let's look at the Euler Lagrange equation. And of course, now we have a y as an independent variable. So we need to adjust this equation, right? Because in this form, equation is not correct. Because in this form, x is independent variable. In this equation, x is an independent variable. So for this situation, it will be, of course, now df over dx, because now x is dependent. So instead of df over dy, now we have df over dx. Then will be minus d over dy, because now y is an independent variable, d over dy, and partial derivative of f with respect to x prime now. That's the correct Euler Lagrange equation for this situation. And now again, let's look at this second order differential equation carefully. df over dx. Function f is not a function of x. There's no explicit dependence. So it means df over dx immediately 0. And immediately it means that we do the first integration automatically. We don't have to sweat. So we can skip the first integration. Again, in both cases, you will end up with the same answer. That case or this case. But obviously now, in this case, you will have to sweat much less. In the first example, in the first situation, yeah, you will probably double the amount of your integration time. Right? So be careful at this point where you have to make a decision which variable should you treat as independent and which one is dependent. Pause, right, and imagine your function and Euler Lagrange equation and make a decision, because it will simplify your solution tremendously. Right. Okay, so obviously we're going to use the second option. Right. So this is our integrand. Why you keep saying integrand? Functional. And of course, then we will have to use integrand, extract from that. So, all right. Of course, let's use second option. Right. Of course, in this case, function f. Let me rewrite it. So f. This factor in front, you can forget about the factors, because it will appear on both sides of this differential equation. It will be here and there, so you can cancel because it is equal to 0. So factors in front, not that important. So I can drop that factor, and as a result, function f, let me write, it will be square root of 1 plus x prime squared divided by y. Okay, so that's the integrand. Finally, I pronounced integrand at the right time. All right, and our Euler Lagrange equation. So in this case, df, okay, you know what, let me complete this just to show that this is now 0. Right, so now this is 0 and put a big happy face. Right. Okay, so now, yeah, of course, since df over dx equals 0, so immediately it means that partial derivative of f with respect to x prime is constant. Okay, let me write so first d over dy df over dx prime equals 0. And again, like in the previous lecture, I emphasized on that because some students still do it. Don't differentiate with respect to y, right? Because again, you will go back to the second order differential equation. It's just redundant work, right? Of course, in this case, df over dx prime is just a constant. Right? So df over dx prime is a constant. Df over dx prime is some kind of constant. Right. So right now, I'm not introducing some particular form over the constant. I will do it in a couple of minutes. So let's differentiate with respect to x prime. So it will be 1, right, square root will go downstairs. We'll have square root of y, then square root of 1 plus x prime squared, right? Then 1 over 2 in front, right? Because we're differentiating square root, so it will be 1 over 2. And then we need to differentiate what is inside. So we differentiate with respect to x prime. So x prime we have squared. So we'll have 2x prime upstairs. So times 2x prime, right? So it is equal to that constant. Of course, 2 goes. Okay, so the next step, of course, whenever I see square roots, they make me feel uncomfortable. So every time I try to square it to get rid of them. Right. So let's square. Of course, we will end up with x prime squared divided by y and times 1 plus x prime squared and equals to constant. Of course, it will be different constant, but at this moment, I'm still write it as a constant. And I think at this point, in order to make the best looking equations at the end, let's call this constant as 1 over 2a, where a is some constant, right? So I think it's at this point 1 over 2a. Let me check if I correct, but I think, yeah, it's that point. Yeah, it's that moment. Okay, so now let's solve it for x prime. First, it will be, okay, I think I should be able to solve. X prime will be square root of 2. Y will be there, so it will be y upstairs, and then 2a minus 2a minus y, 2a minus y. It looks like, let me check to make sure that I didn't make any mistakes. Yeah, y divided by 2a minus y. And of course, again, you remember x prime, it's a dx over dy. So it's, of course, dx over dy. This differential equation is called the cycloid differential equation. It's a typical cycloid differential equation, right? So it's called cycloid differential equation. Very typical. Okay, let me frame it, right, but with black sort of. It's important to mention, but we need to get the answer. All right, so now we need to integrate it. Y and y over here, so we need to separate variables. Of course, we will end up with x equals to square root of y 2a minus y dy. Indefinite integral. There are no upper and lower limits. We will get constants of integration. We got already the first one after first integration, which was basically given for free. And of course, now we will get the second one. Now, this integral is kind of not very trivial, right? And if you don't know the correct substitution, you might struggle a lot before you will find the right substitution, right? So let's just use a substitution which people found to handle this integral. So substitution is y equals a1 minus cosine theta. So substitution. So we're moving from y to a new parameter or new variable theta. Okay, am I correct? Yeah, that's correct. So now we also need dy, so let's take dy. Right, dy will be equal okay, this is minus, so a sine theta d theta. Okay, so let's plug it. Replace it. And we will end up with square root of y, it's a1 minus cosine theta, right, divided by 2a. 2a minus this. If you open the bracket, it will be 2a minus a. It will be a, and that minus, with that minus, give us plus. So downstairs, we will get a plus a cosine theta. Right. So we'll get a 1 plus cosine theta. Right. I didn't make a big step, right? So it's just you plug it here, subtract, and of course you will end up with this. Okay, I'm not writing dy for now because, okay, maybe I will write, but I will step away. So dy is a sine theta d theta. Now, in order to simplify it further, let me multiply both upstairs and downstairs but by 1 minus cosine theta. 1 minus cosine theta, and here 1 minus cosine theta. And now I can close my square root. Okay, so this can be cancelled with that, so pretty much it's the same as that. But now, 1 minus cosine, 1 plus cosine theta times 1 minus cosine theta. It's a 1 minus cosine squared. 1 minus cosine squared, it's a sine squared. And if you take a square root, we will get just sine function. This sine function and that sine function, they cancel each other. Right? Okay, so let me emphasize that this will give me, sine squared theta. And of course, that will be cancelled with this sine. Of course, this a can go. And upstairs, we have 1 minus cosine squared. So again, that can be taken outside of the square root. So as a result, we're getting very, very nice outcome of this. So it will be still a here. A 1 minus cosine theta, right? As I said, now it can go outside, and d theta. Very nice substitution, and integral basically, integral falls apart. But again, if you don't see this substitution, you can struggle with this integral a lot. All right, so integration of this is trivial. Right. So we will get a theta minus sine theta and yeah, no, hold it. Oh no, it's correct. Why? I don't know why I started doubting myself. No, it's correct. And plus some constant. Of course, now this is the second constant of integration. It's still second order differential equation. Okay, now I can erase this. Yeah, I need to erase this. And so now this is what we found. This is x. You see, x equals to this, right? So let me rewrite that. X equals a theta minus sine theta plus constant. And where is y? In our substitution, right? Replacement. So basically, we have parameter. Okay, we wrote the equation in the parametric form, parameterization. So y equals, where is a, 1 minus cosine theta. So that's parameterization. Okay, we have that constant, this. Yeah, so two constants of integration, a and that constant. Of course, they can be found using the endpoints, right? This and that. So we know initial conditions. So let's apply in order to find this constant. So we know that when x equals 0, y equals 0, because we position the origin at the initial point, right? So now let's apply initial conditions that x equals 0. Okay, x equals 0, and at that point, y also equals to 0. Right? So y equals to 0 can be used to find the value of this parameter theta at the moment when the system is at this point. Right? So now we have this theta parameter, so we have parameterization. So the value of theta at this moment, at this point, so y equals 0 equals a 1 minus cosine theta. So of course from here, obviously, you see that theta must be equal to 0. Right. Okay, so at point 1, theta equals to 0, and now, of course, we should be able to find x. So x equals to 0, right? Equals, and now we know the theta. So a 0 minus, okay, it looks like theta, let me write, it's a 0. Minus sine of 0, which is 0, and plus constant. So immediately you see that constant is 0. So we apply initial conditions, initial position, and we found that this constant is 0. So now we can write the final form of the equation. I need this. Okay, not that much. I can sacrifice it. Right. When I need it, I will just redraw quickly what I need. These new markers difficult to erase at the very beginning. Very sticky. Right, so now the final form of the equation, x equals a theta minus sine theta, y equals a 1 minus cosine theta. So that's the equation of a cycloid in a parametric form. So which way I wrote it? Parameterization of a cycloid. Parametrization of a cycloid. So basically, this is the equation of cycloid. What is cycloid? I'm sure that you probably seen it in the past in some of your classes. So if you, for example, take a wheel, right, and take a, put a dot on the wheel right over here, let's say, maybe it's difficult for you to see, and start rolling it on some surface. And if you follow that point, the track of that, if you try to keep track of that point, that point will draw a cycloid. Will draw a cycloid. Okay, so let me draw, but I'm going to draw it this way. So if you roll the wheel at the ceiling, on the ceiling, right? As a result, you will end up with this curve. Right, so let me draw a long line. Let's say this is the ceiling, right? And again, pick a point on the wheel and roll the wheel. That point will draw something like this. Okay, let me use maybe blue. Right. So it will be something like this. Then, and so on. So that's a cycloid. Of course, it's very kind of rough sketch, right? But that's the cycloid, and of course, point, let's say, will move that way, and of course, the point moved also that way. So our case, basically, our point 1 was here, and point 2 was somewhere here. So if you use a cycloid between point 1 and point 2, and of course, don't forget, in the presence of the gravity on the surface of the Earth. So you need to use a cycloid in order to minimize time. You remember, we're trying to find the path along which the travel time will be the shortest. Okay, so we solved the problem. And now, before we go to the next example, let me mention one spectacular property of this cycloid. Really, really impressive. So let's look at this point, this minimum point, right? Stationary point. Let me call it point 3. And it has amazing feature. Let's say I release the cart. Okay, let's say it's a roller coaster track, right? No friction, of course, right? So if I release the cart from this point, and let's say it will take 2 seconds to get to this minimum point. So from this point to that point will be, let's say, for example, 2 seconds. Then, if I move the cart even farther away, and again release it, it will get to this point 3 in exactly the same 2 seconds. If I release it from this point, it will still take exactly the same 2 seconds to reach point 3. If I release it from here, again, still exactly the same 2 seconds. It's amazing, right? Really, really fascinating. Of course, you understand, because if you release it kind of farther away, it will just acquire larger speed. Of course, the sort of distance longer, but at the same time larger speed, so time stays the same. But if you release it here, kind of speed is small, although at the same time distance is small, but still takes exactly the same amount of time. Right? So it's actually a really, really impressive feature of this curve, of the cycloid. And as a result, as a consequence, look, what if I decide to create an oscillator around point 3? It's a stable equilibrium point, minimum, right? So I should be able to create an oscillator. For example, like, again, a roller coaster car. I release it from here or from there. Of course, it will start oscillating. And what is amazing, the period of oscillations that does not depend on amplitude. So it doesn't matter if it oscillates like this, from this point to that point, or between this point and this point, period will be the same. So this is truly isochronous the motion is perfectly isochronous. Basically, it does not depend on the amplitude. Right. So let me look, what should I write? So oscillations of the beat oscillations of the beat or of the card are perfectly isochronous. Where else have you seen similar to this, but not exactly, not exactly? You remember the simple pendulum? Simple pendulum, mass, chord, right, and the mass oscillates. It is isochronous, but under only certain conditions. If you use small angle only, in a small angle approximation. So if you have a pendulum, if you displace it slightly, angle is small, then yes, the period will be, the oscillations are going to be isochronous, and the period is going to be sort of amplitude independent. But again, if amplitudes are very small, displacements are small. If you, of course, displace the pendulum by a large angle, of course, the period will depend on the amplitude. But in this case, exactly isochronous oscillations. Period does not depend on the amplitude. Very interesting curve, cycloid. And this feature is, yeah, truly amazing. Okay, so let me write something about that. Right, okay, so I can erase this and write about these oscillations. Right. Oscillations of, okay, let me write, so oscillations of a card or beat, right? It depends on the system. It can be, for example, just a wire shaped in the form of cycloid and a bead, right, which can slide without friction, right? So, or a roller coaster card. So that's why I use both words. Of the bead along the path, along the path are exactly isochronous. Let me check if I spell it right. Yeah, isochronous. Period perfectly independent of amplitude. So it means that period perfectly independent of amplitude. Yeah, really, really amazing curve. Line. Okay, so that's the second example. Just to show that we can basically use this tool to minimize anything, right? And again, we cannot, strictly speaking, guarantee that it will be minimization, right? But again, as I said, in all the examples that we are going to see, and most of the time, it is about minimization. All right, so the first example, like which we discussed in the previous class, we minimize distance between 2 points. Now we minimize time. And now next example, let's try to minimize area. As I said, you can minimize potential energy, volume, right? There are tons of possible situations. This example, I will just set the problem up, and then it will be your homework, right? It's actually problem 619, right? I guess I can, yeah, I'll probably erase that. Maybe, why not? No. I want to keep this, so let me erase that so that I can compare. So in this problem, we have two arbitrary points in 3D space. Let me draw the picture. It will be easier to explain with a picture. So it's a 619, and then I will write what are we going to minimize. I will write. So we will minimize now. Minimize an area. So let's assume that we have coordinate system, right? Y, x, right? And then, as I said, let's assume that we have two arbitrary points. Let's say here, yeah, let me put it here and there. So point 1 and point 2. Then, if you take a completely arbitrary, again, path, like what we've been doing in the previous two examples, like what we did in the previous two examples. And now, okay, so we have this thing. And now if you start spinning this curve around x-axis, right? So you see this curve, and if you start spinning around x-axis, of course, you're going to get what is called the surface of revolution, right? So the problem is, we need to find the shape of this curve so that surface of revolution would be minimum. Right, so again, we picked a completely arbitrary curve. And if you start spinning, of course, you will create some surface of revolution. And so we need to adjust the shape of this curve so that the surface of revolution will have a minimum value. Interesting problem, right? And of course, if you don't know this tool, if you don't have this tool, it sounds like ridiculously complicated. But with this tool which we developed, right, calculus of variation, it's very straightforward. Right. Okay, so minimize area over surface of revolution of a surface of revolution. Surface of revolution. Right. So first example, minimization of distance, then time, and now the surface. Okay, so let's draw so the surface of revolution with this arbitrary y of x. Right, so it will be approximately here. That point will be there. So, right. Yeah, sounds correct. In terms of dashed line and solid lines. Okay, so again, this is arbitrary y of x, and then of course we need to adjust it to minimize this surface. So we need to first set up a functional, again an integral which represents a quantity which we want to minimize or make stationary. In this case, since we want to minimize area, so we need to write down an integral which gives us an area of this surface of revolution. And again, you need to understand, we're talking about only this surface, kind of cylindrical surface. Okay, distorted. This front side and back side, no. We're talking only about the surface of revolution. All right, so we need to set up the integral, and it should be quite straightforward. So what we need to slice this surface into small rings. All right, so let me take here, for example, small ds, right? Which here we have some point x, this point y, just completely arbitrary ds. Of course, around x we have dy's. This is almost horizontal. Okay, you understand. So this is x, and then of course around that there is a dx, and of course around that y there is a dy also. Okay, so but I don't want to write this because I will. Okay, let me erase it. You understand that there is a dx around x. I just need this space for something else. Right. Okay, so let me draw this ring. Of course, over there it will be a dash line represented by a dash line. So small slice of this surface, small ring, of height or width of ds, and radius y, right? Since we're spinning around x-axis, so the radius of this ring is y. Right. So let me show that this is y. So that's why I didn't want to, that's why I raised those x's and dx's, because I knew that I need to write all that. Okay, so now obviously, so we know how we can write this area. Okay, let me highlight this. This is dA. Right. So the area of dA, obviously. So it's 2 pi r, but in this case r is y, right? Because we have a circle here, right? So it's a 2 pi y times the thickness, which is ds. So it will be 2 pi y and ds. So we just need to write ds explicitly, right? Okay, I will start writing area. So area equals, of course, integral of dA, integral of 2 pi y, and instead of ds, of course, again, dx squared plus dy squared. Right? Again, from point 1 to point 2. Right? Okay, I thought about framing it, but it's not the final form of the functional. Because again, we're at the same dilemma. Which variable should we treat as dependent and which variable should we treat as independent? Okay, let me. First, I thought about giving it completely as a homework, but let me discuss it quickly. So the same dilemma. Right. So if we, which case I will look first? It doesn't matter. Let's start with x independent and y dependent. Of course, in this case, the function f will be what? Y square root of 1 plus y prime squared, right? If you take, I thought about skipping the, okay, yeah, you can see it immediately. So if you take dx outside, we will have a 1 plus y prime squared. Right? So that's the integrand. And, of course, our Euler Lagrange equation, like over there, that's why I didn't want to erase that. df over dy minus d over dx and partial derivative of f with respect to y prime equals to 0. And in this case, again, very sad story, this is not equals to 0 because there is a y dependence. Again, it's not a crime, it's not, there's nothing wrong with that, it's absolutely correct. And I solved this problem using both methods. Using this x as an independent variable. It took me the whole page of careful integration because now you have to integrate it twice. All right? So again, you can get the same answer. It's not wrong, but it's just more work. And in the second case, right, so that's the first case. Now the second case, what if y independent and x dependent? In this case, integrand will be, sorry. So now we'll take y dy outside, so we'll have 1 plus x prime. So it will be y and square root of 1 plus x prime squared. And again, you see factor of 2 pi, I don't even bring it here because again, in the Euler Lagrange equation, it will be just canceled immediately. So we don't need those factors constant. Okay, so in this case, again, so now, of course, we need to write Euler Lagrange equation properly. So it's a df over dx minus d over dy and partial derivative of f with respect to x prime equals to 0. So now df over dx 0, because we don't have, again, it's a partial derivative. Yeah, we have here x, but it's a x prime. So it's a partial derivative with respect to x. So this is 0, and of course a happy, satisfied smile. So this will be your homework. So if you want to torture yourself, okay, go ahead with x being independent. And this approach is probably 4 times shorter. It took me like a quarter of a page to solve this problem, right? But of course, this way, pretty much the whole page. Okay, the way I write. Okay, so that will be your homework. So we looked at 3 examples, basically. Again, minimization of a distance, then minimization of a time, and now minimization of a surface. Again, you can minimize volume, potential energy, some expenses, right? You can minimize whatnot. So it should be enough. About chapter 6 is basically like 1.5 classes, close to 2 classes. And now, after this, we are ready to start introducing Lagrangian formalism, because these tools, most of these tools of calculus of variations are used, it's better to say it this way. Lagrangian formalism uses tools, right, or based on tools from calculus of variations. So you will see, we will utilize our Euler Lagrange equation, and you will see. Right, okay, so now I think I should start erasing this. Okay, at least I will be able to start introducing. So first of all, what are the advantages and disadvantages of Lagrangian formalism? So let me first write the title. So now it's a chapter 7, right? Chapter 7, Lagrangian formalism. Right. Even before we start writing advantages, of course, I will write them. So now we will have, after introducing Lagrangian formalism, we will have 2 alternative formalisms, completely independent. Newtonian approach doesn't care about Lagrangian. Lagrangian approach can live happily without Newtonian approach. They are not dependent on each other, right? They do not depend on each other. All right, so any problem can be solved using either that approach or this approach. And Newtonian approach, of course, is based on Newton's laws, right? And of course, an equation of motion, it's a Newton's second law. So in Newtonian approach, we have something like this. So we have some building, right, construction, right? And the foundation is of this approach Newton's laws, right? Foundation, Newton's laws. That's the foundation. Again, you remember, like Newton's second law, no one can derive it. We just accept it. You remember, we're like a church of believers in Newton's laws, right? So, yeah, that's the foundation. And then using that foundation, we've developed the whole structure of a Newtonian approach, right? So that's Newtonian formalism. Now, in the Lagrangian formalism, again, it should be structured in the same way. So there must be foundation, which we accept as axioms, right? Cannot be derived. Just it is written based on observations, and then based on that foundation, you should be able to build the whole construction of the formalism. Right? So in the Lagrangian formalism, everything is based on what is called Hamilton's principle. Probably next class I will present it. So it's based on Hamilton's principle. Hamilton's principle. Right. So that's the foundation. And then using logic, using some calculus stuff and everything, you can build the whole building of this formalism. That is, of course, as I said, Lagrangian formalism. So that's Lagrangian formalism. Okay, so, and of course, strictly speaking, from the theoretical point of view, of course, we need to grab Hamilton's principle and start and derive equation of motion and so on. But we are going to do some voodoo, right, in order to introduce Lagrange equations, right? Why we're going to do this finicky stuff? Because from educational point of view, it's better to connect everything. So the new material must be based and connected to the previous. So link everything, link everything. Right? But of course, as I said, these are two completely independent structures, right? So everything that we have here must be derived from the Hamilton's principle. And that's what we usually do in the graduate level course. But here, again, from educational point of view, since it's the first time you see Lagrangian formalism, we're going to introduce Lagrange equation in a finicky way. We will just basically dig up a tunnel from the Newtonian approach to the Lagrangian approach. And using Newton's second law, we're going to present Lagrange equation. Okay, in a second I will start doing this, but now let me first state advantages of this formalism over that, formalism over this one, and then we will start digging up the tunnel and to derive Lagrange equation. Of course, it's not a derivation. Derivation must be done from the Hamilton's principle. All right, so let me state advantages. All right, so advantages. So first, in Newtonian formalism, everything is based on forces, right? Free body diagrams, of course, must be written. But in the Lagrangian formalism, everything is based on energies. Every time we will have to write potential energy, kinetic energy. It's all about energies. So, of course, it's much, much easier to work with energies because those are scalar functions. I don't have to convince you in that, right? So, first advantage. Number one, so easier to work with energies. Easier to work with energies. Right, so advantage number one. Then, second, easier to deal with constraints. For example, some surfaces, right? So in the system, jumping, screaming, I know, doing something on that surface, right? You will see in the Lagrangian formalism, it's easier to deal with constraints. We will just take care of those constraints at the very beginning of the problem when we write down the Lagrangian, and then after that we can forget about those constraints. It's much easier to work with constraints. So easier to work with constraints. Right. Surfaces, rods, right, so whatnot. And the last one, okay, probably the most appealing, Lagrange equation, which will be equation of motion in the Lagrangian formalism, has exactly the same form. It doesn't matter which coordinate system which coordinates you use. If it's a Cartesian coordinates, you will have x's and y's, right? Or x and y's and z's. If you move to I don't know, polar coordinates, just replace these x, y, and z with r, phi, and z. If you move to spherical coordinates, just replace those x, y, and z with r, phi, and theta. If you go to some parabolic coordinates, right, just replace with those coordinates. If you go to hyperbolic or whatever coordinates you feel comfortable using for that particular problem, just replace. The shape of the Lagrange equation is going to be exactly the same. That's probably the biggest beauty or advantage of the Lagrangian formalism. You remember in the chapter 1, in the Newtonian approach, when we decided, okay, to write down Newton's second law in just simple polar coordinates. And I spent like, I don't know, 20 minutes getting through those calculations. In this case, you don't have to do that. Of course, it can be proved, right? And I saw the proof, right? And I read, it's pure calculus. Tedious, maybe like 20 minutes of tedious massaging. I decided, no, I'm not going to prove that form of the Lagrange equation stays exactly the same. Right? So we're just going to state it and use it. Right? Because again, the proof is very, very tedious, right? Not much of a physics, except for calculus. So the last one, the form of the Lagrange equation stays the same. Of course, you still don't know which form, but we will write in a second. The form of the Lagrange equation of the Lagrange equation stays the same. Stays the same. Okay, so these are advantages. Okay, so now let's, as I said, let's dig up a tunnel, right? So some kind of tunnel from here to there, right? And let's crawl from that approach to that approach. Again, it's only makes sense from educational point of view. Otherwise, yeah, it's too finicky, right? Okay, I will put a new bullet. And let's get Lagrange equation, the Lagrange equation from the, okay, let's get the Lagrange equation. So let's start with the simplest possible situation. Let's say we have a point mass, all right? No constraints, so no surfaces, no rods, or nothing which would restrict motion of that point mass. And let's assume, three-dimensional space, and let's assume that it is exposed to some conservative force. So as a result, we can introduce potential energy. Right? So let's consider a point mass M in 3D space, and force is conservative, and F, of course, is a function of R, is conservative. So there is some force, of course, external force, because it's just one point mass. So we can introduce potential energy, of course. Conservative, so we can introduce potential energy, U as a function of R. Potential energy. Right. So maybe you can draw something like this. So we have three-dimensional space, some point mass, right? R, and exposed to some force, right? So F, which is conservative, some field. All right, and now, just for fun, out of the blue, without justification, right, let's consider. Right, so now let's consider for fun. This function, L, and I will use this wavy L, as kinetic energy minus potential energy. I don't know, maybe I can say I like subtracting potential energy from the kinetic energy, right? to justify, right? There seems to be no good reason why we should consider this. Of course, it can be derived, again, from the Hamilton's principle, and we're going to do it in the graduate level course. But for now, we're just digging up the tunnel to get from what we know something new. So just for fun, let's consider this strange construction, kinetic energy minus potential energy. Of course, we can write, oh, why my cell phone didn't ring? Okay, so let me write the potential, I mean the Lagrangian, and let's call it Lagrangian. And then next class, we will take from here, right, and get the Lagrange equations. So, and it's called the Lagrangian, or Lagrangian function. Right, and so let me write, so L equals, of course, it will be 1 over 2 m x dot squared plus y dot squared plus z dot squared. As I said, we have three-dimensional space. And minus potential energy. Force is not given explicit form, so just saying we have just completely arbitrary potential energy. Minus u, and of course u is a function of position only. So the whole dynamics is here in kinetic energy. Static is there in the potential energy. So from here, we will continue next class.
In the sky.